Assalamu alaikum. Welcome to the third lecture of data mining. So I hope all of you are doing well. So this is the second week of the semester and we are into the third lecture. So we were discussing chapter 2, which is about data understanding. So today we will continue with this discussion and we will be covering, we will be talking about data understanding in terms of numbers. We will look at the central tendency, we look at the dispersion tendency, we look at some graphs of visualizing and understanding data. And then after that, we'll move on to chapter 3, which is on data preprocessing. And data preprocessing has a number of distinct steps, and we will be discussing each one of those in the following two lectures. We will maybe start today, and then in the next lecture and the following lecture, we'll be covering data preprocessing. So that's the agenda for today. So I have uploaded a Word document on LMS resources. This Word document has linked to some websites. These websites basically are supplementary reading stuff for your content. So they basically talk about things like text preprocessing or data preprocessing. They will talk about, for example, later on we'll talk about association mining, discuss some case studies for association mining, for example, or discuss some specific algorithm like FP growth. So these are in addition to your textbooks. You can spend time reading on the web and supplementing your understanding of data mining concepts and techniques. We have also uploaded a tentative schedule for the semester. So this is tentative, so just to give you a heads up. And I think a assignment not an assignment 0 has also been uploaded just to make sure that everyone understands Python and its use, because that would be the primary language used in the assignments in this course. All right, so are there any questions? All right. So I'm basically under the weather today, a bit of a sore throat and some runny nose. So I might be a bit slow as well as sluggish today. So we talked about the basic data matrix, which is a 2D representation of data last time. We said that rows were columns and they represented data objects, and columns were the features for each data object. And we can call these terminologies by different names as well. So features or variables or attributes and so on. So subsequently, we talked about attribute types. And the most common classification, categorization of attribute types is nominal, ordinal, interval, scale, and ratio scale. So this is a common categorization of attributes. So why do we want to categorize attributes? Because we want to get some idea of their characteristics and properties. So for example, nominal attributes can be matched or compared exactly, but you cannot rank nominal attributes. So ordinal attributes can be ranked, but you cannot apply other algebraic operations on ordinal attributes. So interval scaled attributes, you can apply some algebraic operations, but the division operator typically gives misleading results for interval scaled. While ratio scaled attributes are the most expressive. So this is also a range from nominal, which is the least expressive or least informative, to uh, ratio scale, which is most expressive or most informative. And of course, you can apply most operations on ratio scaled attributes. So there was another categorization called discrete versus continuous. And of course, these categorizations can overlap. So just trying to highlight again. So let's say if you have a variable, let's say color. So discrete would have a finite set of possible values. So for example, R, G, B. So this is an example of discrete attribute. While if you talk about a real valued attribute or continuous attribute, for example, so let's say if you talk about, let's say, age, so this would be a continuous value in the range 0 to, let's say, 100. So I'm basically using math notation to define the range or the domain of each attribute. So this is the difference between discrete and continuous. So discrete has a finite set of possible values. Continuous may have an infinitely possible set of values, and they are usually numbers. And we specify them as ranges, or even from pure mathematics, you can specify in terms of, for example, the real positive real value. So weight could be the positive real value. All right. A few things again regarding structured data. We are talking about data matrices right now. So these are some of the things that you need to think about. Some other things that you need to think about is the dimensionality. So dimensionality basically is, if you which difference between which two? Okay, अच्छा ठीक है. I think you can look at the previous videos. The videos are also available on YouTube, and you will get an idea about these attribute types if you have joined late in this class, in this course. अच्छा. All right, so dimensionality basically refers to the number of attributes describing the data object. And you might have heard about the word, the curse of dimensionality. So if you have more attributes or variable describing objects in your data set, then you need exponentially more examples to properly characterize those objects. So this is called the curse of dimensionality. So in general, if you have a data set that describes a few number of attributes, you might be okay with a small data set, let's say with a few hundred examples. But if you have a data set with hundreds and even thousands of attributes, then to properly characterize the relationship between all those attributes across the data set, you would need a lot more examples, maybe in the tens of thousands, hundreds of thousands, even millions. So this is basically called the curse of dimensionality. So you need to be aware of the issue of dimensionality when looking at data set. The other issue, I'm going over these fairly quickly because these aren't, we're not discussing these in very, I would say, detail, because these are things that you need to look into, understand, and move on. So sparsity. The sparsity basically refers to the uh, actually this is somewhat related to dimensionality. It's kind of opposite to that. So if you have a very uh, high dimensional data set, then it would tend to be sparse, meaning that you might have in the space, in the data space, you might have regions where you have very few examples. So sparsity in general means that you need to know in which regions of your data set you have fewer examples, in which regions of a data set you have more examples. And if you have lots of regions in which there is fewer examples, then you would know that your data set is not sufficient for analysis. So that is sparsity. So then we have resolution. So resolution basically refers to, you can say, granularity. So for example, is your data aggregated or raw? So that is one example of granularity. Do you have information about the highest level of granularity or at a lower level of granularity? So for example, if you are talking about, let's say, uh, student data at LUMS, for example, if you have information about the average grade for students in each course over the past 5 years, so that is lower granularity. But if you have information for every student in every course over the past 5 years, that would be higher granularity, meaning that the resolution is better and you might be able to do more advanced or sophisticated analysis on that. So you need to have an idea of resolution as well. Uh, Finally, you also have a notion of quality, which we'll discuss in more detail when we start talking about text preprocessing. So you need to be at least qualitatively, if not quantitatively, assess the quality of the data. And quality, as we'll see, means accuracy, means you can also say precision. We will discuss these two terms shortly. And it can also mean whether it is complete or it has missing values. It is whether it is uh, timely or not, whether it is believable or not. We'll talk about these terms later on. So these are some of the terms by which you need to look at your data and try to understand them. So just very briefly, we often use the word accuracy and precision. And these are, of course, related to values, attribute values, the values that you give to attributes. Okay? So accuracy is, it's actually referring to, so how close is the measured value to the true value? How accurate is the measurement? So let's say if you have a an item, let's say if I talk about an item like a laptop, and you weigh it on a scale, right? So let's say its true weight is 1.3 kg, for example, but you use a scale and measure it. The measured value, let's say, is, let's say 1.5 or let's say 4. kg. So the difference between the two is referring to the bias, you can say, in the measurement. Of course, when we use the word bias, if this error is more or less consistent in your measurement, which typically refers that your scale is biased. But in general, accuracy means that how far away is your measured value from its true value. Okay? So that's accuracy. And you need to have an idea about the accuracy of the data that you are working on. The other thing that I want to talk about precision. So precision is basically talking about repeatability of measurement. So in many cases, you might have multiple values recorded for a particular attribute of an object. If those multiple values are very close together, meaning that, let's say, if I talk about my laptop, so 1.3 plus minus, let's say, 0.05, meaning that the measured value would only range between this interval. So 1.25 to 1.35 plus minus 0.05. So this interval in which the value lies is a quantification of the precision. The smaller this interval, you mean that the higher precise or more precise your value is, or you are measuring processes of high precision. So precision typically refers to repeatability. If you have multiple values, how are those multiple values close to each other, not with respect to the true value. So it might happen that maybe your instrument is biased and it is giving a value of 1.4 plus minus 0.05. So this is high precision, let's say, but low accuracy, because true value was 1.3. Okay, so you need to be aware of the distinction between the two. All right. So moving on, so we had talked about attribute types, and we have talked about some characteristics of such attributes and data sets. So now let's try to get a better idea of these attributes and their values in the data set through some measures. So we talked about central tendency last time, and then we also have what is known as dispersion tendency. So in other words, we want to find what is the single value that can best characterize a particular attribute in a data set, the best value. So that would be given by the central tendency. And of course, if you want to know the distribution, idea of the distribution, that would be the dispersion tendency. So for central tendency, the three values are mean, median, and mode. You are familiar with these ways of finding the central tendency. So some characteristics of these values, of course, mean can be computed for numeric attributes, attributes that are interval scaled as well as ratio scaled. Mean cannot be computed for nominal or ordinal. Median can be computed, of course, for ordinal as well. And mode can be computed for nominal as well. Okay. So which measure generally is considered to be less prone to, let's say, skew? Actually, that's a more technical problem, but still, so if you are given, for example, the median, and you're also given the mode, mean, which one would better characterize a central tendency if you have both of these values? So generally, median is considered a better representation of the central tendency because uh, you're taking the value that lie in the middle of all the values when they are ranked. Okay, so median is generally considered more robust measure of the central tendency of a attribute. And of course, you can compute mean as well, but mean and median would deviate from one another if the data set is skewed. If the distribution, let's say, there are more values, higher values, and lesser, smaller values, the mean would move towards the higher value, while median would still remain in the middle. So you need to know this distinction when you're looking at these values. So, okay. So moving on to the dispersion tendency. So you are familiar with the measures in this category as well. If your data set is so if your data set is, let's say, numeric, interval scaled, or ratio scaled, uh, you can use what is known as the standard deviation, right? The standard deviation would give you a measure of the dispersion tendency of the data set. So all of you are familiar with the standard deviation. So standard deviation is computed as the weighted average of deviation from the mean of that attribute. Uh, so standard deviation usually is represented, let's say, using sigma. The sigma, let's say, of an attribute, let's say age. If this value is, let's say, I would say 5. So what does this mean? So this typically means that, of course, would relate to the distribution, but in rough terms, it means that the majority or vast majority of your ages would lie across the mean plus 5 and minus 5. So mean plus minus 5. So 5, the unit of 5 is the same as the attribute. So let's say if you're talking about age, so it has the same unit. If you have, we are talking about weights, for example, in kg, the unit of the standard deviation would also be in kg. So if you have two data sets, let's say you have, you're taking the STD of age of students, and you get a value of 2, for example, STD of age of, let's say, employees, and let's say you get a value of, let's say, 8. So you know that employees have a wider spread. Its dispersion tendency for the employees in terms of age is higher. All right. So what about, so this can be done for interval scale. And ratio scaled. So if you have attributes that are ordinal, meaning that they have order, but you can't really compare the scales between two ranks. So if that is the case, how would you determine the uh, dispersion tendency? So for this, you can typically use what is known as called a quantile. And there are actually many variations of quantiles. So you might be familiar with some of them. For example, percentile. The percentile and quantile basically is the same thing, only that one is expressed as percentages, the other is expressed as fractions. Okay. So what is the quantile? Let's first talk about uh, percentile, or let me just start with quantile first. So for example, let's say you have any attribute. If you rank that attribute's values, you can compute the percent quantile for each value in that rank. Let me just take a the question was what? Algebraic sum on which data? Interval scaled. Yeah, you can apply sum on interval scaled. So there isn't any issue. All right. So percentile, or let's say quantile, for example, let's say take an example. I'll just use rank. Let me use numbers actually. 10, 15, 18, 20, and 25. So we have five objects, and let's say rank would be 1, 2, 3, 4, 5. So you have to order them. So I'm writing the rank below it. So if you want to find the quantile for the first rank, which is the value 10, so the usual way to do that is basically you take the rank, which is 1, and then you minus just a small number 0.5. This is a force convention, and divided by 5. 5 is the total number of observations. So the rank becomes 0.1. So this is the quantile for the first value. So let me say the third value. The third value quantile would be 3 minus 0.5 divided by 5. So this is the answer that you get. So 0.5. This is a quantile for the third value in this data set. And as you can see, if you multiply these numbers with 100, you get the percentile. So for example, 0.5 into 100, so 50th percentile. So what does that mean? आपका क्वेश्चन मुझे फिर से देखना पड़ेगा. You are asking question again?
Okay. So I was asking, okay, can we sum the responses from a rating scale?
जरा फिर से रिपीट कर दें, आवाज थोड़ी आ रही थी आपकी.
Sure, sir. Sir, I was asking कि जी जिस तरह 1 से 5 होता है, 1 means के most likely और 5 means least likely, इस तरह के जो होते हैं rating scales.
जी. तो रेटिंग्स जो है वो that would be considered as ordinal, because unless if you know okay, the difference between those ratings is the same, then you can consider them to be interval scaled. But the best way is to consider them to be ordinal at best. So you have the order, meaning that 1 is poorer than 2, but we don't know how much 1 is poorer than 2. And of course, you know that 1 is poorer or less, depending on whatever, how you quantify 1, 2, 3. 1 is less than 5, and that less is much less than, for example, 2. But how much less, we don't know. If you take it to be interval scale, then the difference between 5 and 1, that is 4, and difference between 2 and 1, that is 1. So that would give you how much less those differences are. So depending on your problem and your domain, you need to correctly assess whether an attribute values are interval scale or ratio ordinal. So what does this 50 means? 50 basically means that 50% of the data of this attribute or the values of this attribute lie below or equal to, below or equal again is a choice that you have to make if you want to add that equality or not, below this particular value. So for example, the 50th percentile in this data set is what? So 18, and the third value is 18. So if you typically say the 50th percentile is 18, which essentially means that 50% of the data lie below the value 18. Okay. So if you have, of course, percentiles and quantiles can be computed for 18 is our data set, the value 18. So the data was what? 10, 15, 18, 20, 25. We rank our data sets values, the values of a particular attribute. Let's say these are ages, for example. So we rank them, and based on the rank, the 18 is rank number 3. Rank number 3 is 50th percentile, or the quantile is 0.5. And so that's where we got 18 from. So for example, I think all of you are familiar with your grading system. So if I say that 75th percentile score is, let's say, 80. So which basically means that 75% of the people with the even number, we still use the same formula, minus 0.5 and j. So we still use the same formula. So 75% of is 18 basically means that 80% or 75% of the people have a score of 80 or less. Okay. So it doesn't matter. I mentioned the formula. So rank minus 0.5. This 0.5 is arbitrary, but usually we use 0.5 divided by n, which is a number of total rank of number of observations in a data. So that is quantile and percentile. And you can compute these for different points. And there are some important points that are of interest. One is the 25th percentile, which is also known as the first quartile from quarter. Okay. And then 50th percentile, this is known as the second quartile. And by the way, this is also the median. What is defined as the median? The middle value. So 50th percentile is the middle value. And then, of course, the 75th percentile. This is called the third quartile. Okay. So these first and the third quartiles are also sometimes often denoted Q1. So second also could be Q2. Third would be Q3. So in our data set that we had before, if you calculate, so 10, 15, 18, 20, 25. So Q1 basically would be 15. Q2 is basically 18. Q3 is basically 20. Okay. So Q1, 25th percentile, Q2, the median, and Q3, the 75th percentile. Okay, so by computing, especially these quartiles, if you want to do it quickly, you get a good idea of the distribution of the data. Of course, this was a very toy kind of example. So there isn't any distribution, very small number of examples. But just to, or you can compute a number for this. For example, I can compute the interquartile range, which is defined usually for ascending order data sets as Q3 minus Q1. So in our case, in the example that we have, this would be 20 minus, what was that, 1815, which is 5. So interquartile range is 5. So let's say this was one data set, and let's say another data set, I found out that interquartile range is, let's say, 10. So what does these two numbers then show? So the spread of the second data in which IQR is 10 is much higher as compared to the first data in which IQR is 5. So IQR is then a measure of the spread or the dispersion tendency of a data set. And finer details of these can be shown in plots and histograms, which I'll just go to a bit shortly. Let me just finish this first. You can get more visual analysis of these numbers in graphs. All right, so we have talked about standard deviation. Of course, you can also have variance, which is the square of the standard deviation, but we should prefer standard deviation because it is in the same units as the data set. The variance would be the square. So its unit would be the unit square. So you can't really compare very easily in squares. So standard deviation, and then of course using percentiles and IQR, for example, to gauge the dispersion tendency of the data. Okay, then there is another quick way of putting all these numbers together, which we call the 5-number summary. So what is a 5-number summary? For any single attribute, it consists of the mean value, it consists of Q1, it consists of the median, which by the way is what? Q2, it's Q3, then quartile, third quartile, and then of course the max value. So these 5 numbers, if you compute it for any value, you have a reasonable idea of the dispersion as well as the central tendency of the data. Mean, Q1, which is the first quartile, median, which is the second quartile, Q3, third quartile, and the max. So this is called the 5-number summary. So usually whenever you first start exploring your data set, maybe load it into in some programming language, let's say using Python and what you call as pandas, some of these numbers are automatically calculated for you by the system. If not, you can always calculate them quickly and show it against each attribute so that you get a good idea of the attribute and its distribution. So any questions? So let me, any questions? So we have already talked about this. So distribution is basically central and the dispersion tendency of the data. So these are some characteristics that we need to be aware of while doing exploratory analysis. The fifth one I mentioned as, and we will discuss this more later on, is quality of the data. Oops. Okay. So a box plot is a visual description of the 5-number summary. So, and as I said, the 5-number summary is computed for each attribute separately, and it consists of the minimum value, the Q1, the Q2, Q3, and the maximum value. And box plot basically shows this pictorially in a graph. So basically, if you look at the graph, there's a box. So there's a box. The upper end of the box would be Q3. The lower end of the box would indicate Q1. The middle or some line in between would give you Q2 or median. And then you have lines from the end of the boxes to the min and the max. Max up there and the min below that. So this would give you a pictorial view. And here you can get a better idea of the distribution. So for example, if you're, okay, let me see if I can use my pen, although my writing would be terrible. Let's see. So can you see my blank screen? So let's say if you have something like this. So let's say this is a box. Upper side would give you Q3. Oh, just a second. Just a second. All right, so let me draw it again. So let's say you have a smaller box here, and then you have a bigger box here, meaning that this is Q1, you have Q2, and Q3. Actually ये लिख नहीं रहा सही तरीके से. ये आ रही स्क्रीन इसके ऊपर?
Yes.
आ रहा है? अच्छा अच्छा ठीक है. Seems to be, मुझे वो कुछ और फीडबैक दे रहा है. अच्छा, so what I'm trying to say is that, let me show with my hand if you can see this. So Q1 और Q2, let's say इतना space है, और Q2 से Q1 बिल्कुल tight है. What does that mean? नीचे sparsity है, ऊपर density है. Meaning that let's say मैं values ले लेता हूँ. Q1 let's say 10 है, Q2 let's say 30 है, और Q3 40 है. So 10 and 30 is a range of 20 values, or 30 and 40 just a range of 10 values. Meaning that within that 10 values, you have this 25% of the data, as well as within 10 and 30, you have 25% of data. So जब 10 और 30 के दरमियान 25% data, and 10 or 30 or 40 के दरमियान भी 25% data, it means that data is more dense between 30 and 40, closer together, because value 30 to 40 के दरमियान है, और दूसरे में 10 to 30 के दरमियान थोड़ा ज़्यादा spread है. So you get an idea of the spread in each region of the data set. Similarly, जो min max भी आपको बताएंगे, if the max is very far away, इसका मतलब है कोई outlier है, very far away from the Q3. ठीक है. All right. So a box plot, in one graph, you can have actually multiple box plots, especially if you have the same y-axis. तो आप multiple box plots plot कर सकते हैं side by side. Let's say age की आप different ages की आप box plots plot कर रहे हैं, different attributes, but attribute values are age. Then those box plots, you can compare them very easily across multiple attributes. आपको पता चल जाएगा mean क्या है across different attributes. Let's say age of students, age of faculty members, age of staff, and so on. So you get an idea. Mean उसका किस तरह compare करता है, distribution किस तरह compare करती है, min max किस तरह compare करता है, and so on. So it's a very nice way of visualizing the distribution of single attributes and comparing it across attributes with the same range, you can say, or same semantics. For example, age को compare कर रहे हैं. So this slide basically shows you, especially for continuous valued attributes, the distribution of the normal curve. So normal distribution is the standard distribution, and it gives you an idea of how data is spread in the standard distribution. Of course, this is shown in terms of standard deviation. So in the standard distribution, if you take one standard deviation left and right of the mean, that will capture about 68% of your data set. And if you take two standard deviation left and right, almost 95%, and so on. But this is for the standard normal distribution. Your actual data set may not be like this. But in many machine learning applications, we often try to compare and contrast empirical distributions with standard distributions. And one of the most important and commonly occurring standard distribution is the normal distribution, the bell-shaped distribution. So another way of showing distribution is the histogram, and you're all familiar with histogram. So you can divide, if it's a continuous valued attribute, you can divide your attribute into ranges and then count the number of observations that fall in each range. So that will be the height of the histogram. So again, now you get a distribution, an approximation or distribution. So you know in which range, how many examples you have, where it is more dense, where it is less dense, where it is sparse, and so on. Histogram again can be computed for ordinal attributes as well. For nominal attributes, you can plot simply a bar chart. So let's say if you have three possible values, for example, red, green, and blue, number of observations in red, number of observations green, number of observations in blue. Again, you have bars there. So you don't typically call that a histogram, but it's very similar. You are counting the frequency of observations in each category. Okay? So again, you get an idea of the distribution of the data set. So as you can assume, histogram are more expressive than box plots. So box plots are just 5-number summaries, while histograms are distributions for maybe smaller chunks of the data set. While, for example, in box plot, you're only talking about 25% chunks of the data. The first quartile, the second quartile, the third quartile, and maybe the min and the max. So histograms can be more of a higher granularity, and they will give you a better idea of the distribution. So moving to the quantile plot. So quantile, as I said, is, so for example, the quartiles are also based on quantiles, right? So if you want to get a finer analysis idea of the distribution, you can plot the quantile plot. You can have quantiles on the x-axis, or even you can have it on the y-axis, it doesn't matter, and the value on the other axis. And then for each quantile, plot a point and then draw a line through it. So this is similar to a cumulative plot, because quantile is always cumulative, it always increase. So you get an idea regarding, again, the distribution in various segments of the data. Of course, this is much finer grained, higher granularity as compared to, let's say, the simple box plot. So because you now have quantiles at each point of the data set, not at 25% intervals. Okay. So for example, let me see if I can draw something here. So let's say we have, I would say, age here. And my graphing might be poor, but just bear with me. Let's say you have quantile there. So obviously age is increasing and quantile is also increasing. So
Sir, we can't hear you.
अच्छा, ठीक है. अब आवाज आ रही है?
Yes, sir.
अच्छा, म्यूट पता नहीं किस तरह हुआ. मैं was I taken offline कि वैसे ही म्यूट हो गया था?
ऑफलाइन भी हो गया था, फिर उसके बाद ऑनलाइन के बाद म्यूट हो गया था.
हाँ, एक्चुअली यही होता है, बिकॉज मैंने डिफॉल्ट अपना रखा हुआ है ना. whenever I reconnect my automatically it is, I put it on mute. ठीक है. So ऑफलाइन हुआ था, मुझे ऐसे मैसेज नहीं दिया ऑफलाइन हुआ है कि नहीं हुआ. एनीवे, अच्छा. So I was basically trying to interpret quantile plots. So if you have age on, let's say, x-axis, and let's say x-axis पे quantiles कर ले, तो of course दोनों directions पे हो सकता है. x-axis पे quantiles हैं, y-axis पे age है. ठीक है. So quantiles increasing, and let's say quantiles always increase with values. So if you have a horizontal region, now x-axis पे quantile है और y-axis पे एज है. जब हॉरिजॉन्टल रीजन इसका मतलब क्वांटाइल से बढ़ रहा है बट एज वही रह रही है. सो व्हाट डज दैट मीन? मीनिंग दैट के आपके पास देयर आर मल्टीपल एग्जांपल्स ऑब्जर्वेशंस विद द सेम एज, और इन अदर वर्ड्स यहाँ डेंसिटी ज्यादा है. ठीक है. So if you have a slope like this, then it means that there's sparsity. If you go to a horizontal lens, it means that there is density. Because quantile तो बढ़ता जाएगा और values change नहीं हो रही, इसका तो बहुत सारे values एक ही जगह पे आ गए हैं. So let's say 50 की values, there are 10 people with the same age 50. So quantile तो बढ़ता जाएगा 50, मतलब उस एक पहली 50 वैल्यू का क्वांटाइल कुछ और होगा, दूसरे का कुछ और होगा, तीसरे का कोई और होगा, बट एज वुड रिमेन द सेम. So horizontal or close to horizontal line means high density. Vertical or close to vertical line means low density or sparsity. कुछ ये इंटरप्रिटेशन है, ये मैंने अभी बताई है. विद एक्स एक्सिस पे क्वांटाइज है, वाई पे एज है. उल्टा कर दें तो इंटरप्रिटेशन उल्टी हो जाएगी. ठीक है. सो आई थिंक यू कैन डू द रिवर्स एज वेल. ऑलराइट. Okay, now let's so we are so far. So far we have talked about single attributes. So during data understanding, we also sometimes look at two attributes at a time. So just to understand how one attribute varies with respect to the other. So for two attributes, we can, of course, have the QQ plot, which is a quantile plot, meaning that for one attribute, you have the quantile. Slides are not visible. एक second. एक second. अच्छा जी, आज टीए कौन सा आया हुआ है? कौन है इधर? टीए कोई है? लेट मी चेक. आई डोंट नो. So anyway, I just wanted to say कि कोई यहाँ टीए होता है तो मुझे बता दिया करें कि स्क्रीन और ये पहले बता दिया करें, because sometimes I don't get the necessary message here and I didn't know कि I went offline. So वो चीज़ें बता दिया करें. ऑफलाइन के बाद जब मैं ऑनलाइन होता हूँ, typically my audio is also muted because वो मैंने default setting रखी हुई है. I might change it. And also ये screen share भी शायद बंद हो गया था. All right. Okay, where were we? So if you have two attributes, you can plot the QQ plot, which is workable for ordinal attributes as well. And if you have, let's say, nominal attributes, usually basically what you can do is you can basically plot the histogram with pairs of attribute value, which is kind of cumbersome, which is something that we'll find we will be doing in association mining or frequent pattern mining. So we'll discuss that later on. If again you have numeric data, then you can also have scatter plots. So both scatter plots and QQ plot typically works for ordinal as well as higher data types or attribute types. And they give you an idea of how two variables or two attributes vary in our data set. So for example, in the scatter plot, you might find regions of dense values, other regions of low dense value. You might find correlations. So there might be a trend. As one value increases, the other value also increases. So you have a trend like this. It might be negative or it might be positive, or you might have no trend, just like a spherical ball. So these kind of analysis can be done using these plots. Quick analysis. All right. So I think that's what I wanted to cover in chapter 2, because all of this stuff is pretty basic. So we will now move on to chapter 3, which is on data preprocessing. And I'm just going to start this, and I know we are running out of time. So, and we'll continue from here next week, next lecture. So data preprocessing is usually a massive stage in data mining. Massive stage in terms of both time and cost. So it's a timely and costly endeavor in most real-world data mining applications. So why is that? Usually because data is of low quality. And secondly, this is the place at which you would have to do, for example, staging of your data set from multiple sources. You'll get data from multiple sources. You'll have to do some what you call as dirty job of collecting data, conforming it to the form that you want it for your final analysis. So a lot of things are typically done in this stage. So it is usually, as I said, time consuming as well as costly. And it can involve a number of steps. But the point here is that we won't be doing all of these steps for all projects. For some projects, we might do many. For others, we might do a few. So it depends on the project. But since we are covering the theory, so I'll be mentioning all these steps in some order. Secondly, also, it's not necessary that we follow all these steps in the same order. It might be different for different projects. So let me just mention them, and then we'll start discussing them briefly. So, for example, you can have data. So for cleaning, for example, is a task which is directly related to quality. So you want to clean the data. So data integration. So this is about collecting data from multiple sources and making a consolidated repository before doing the analysis. You can have data transformation. So data transformation, whenever you're changing data, both either its structure or its values, it is transformation. So, but there are some specific techniques in transformation that we would like to do to shape our data according to our particular application. So this would fall under data transformation. And then we have what is known as data reduction. So whenever you're trying to reduce your data size, either in the number of values or in the number of attributes, for example, or in some other way, this would fall under data reduction. And you might have one more category, which is called data discretization. And this typically applies to numeric data sets, and you want to convert them into categorical data sets. So you can do this using data discretization. So these are big headings in which you can have techniques, and sometimes techniques for one heading might be used in another heading as well. So, and also I've written them in some order. So this order is not set in stone. You can change the order for any project that you're doing. So the whole idea in the discussion that we do in this chapter, I'll give you what each technique is, how is it applied, maybe some is pros and cons and so on, and we move forward. So this is the idea in this discussion. So you as a data miner later on can make an informed decision whether you want to do apply a particular technique or not. ठीक है. So तो मेरे ख्याल से I will probably stop here. I'm also not feeling very well today. So any questions? Any questions? All right. So any questions? Someone else, one person has responded, no questions. But what about the others? All right. So regarding quizzes, uh, so we will start our quizzes inshallah from next Tuesday. I was thinking of Thursday, but I've moved it to Tuesday. So we will have our first quiz next Tuesday, and the quizzes would be at the end of each class. So this class goes up to 145. So we will probably start the quiz at 135. The quizzes would be on LMS, and usually my quizzes would cover whatever has been covered in the lectures since the last quiz. Okay? So, and of course, it typically would not include that lecture. So for example, let's say आज के क्लास के एंड पे क्विज होता, तो जो आज के लेक्चर में जो नई चीज पढ़ाई गई है वो यूजली मैं उसको डायरेक्टली चेक नहीं करूंगा या टेस्ट नहीं करूंगा. आई विल ओनली टेस्ट दोज थिंग्स दैट यू हैव कवर्ड इन द प्रीवियस लेक्चर्स. सो आई डोंट नो बिकॉज अभी वो डिसाइड नहीं हुआ. कवर तो ऑफ कोर्स डेफिनेटली काफी अभी तेज चल रहा है. एवरी अदर पर्सन सीम्स टू बी इन्फेक्टेड, बट वी डोंट नो. सो मिड अभी तो उसी तरह ही है, 7th वीक के लगभग होगा. फाइनल ऑफ कोर्स एट द एंड. इफ थिंग्स work out well, I think I would like to have the exams on campus. Otherwise, in the worst case, of course, we can always do it online as we did last year.